All right. Well, welcome back to the next one. This one, as promised, we are going to dive into the navigation folder, which is where some of the highest level autonomy exist for this code. Right. So if you can take yourself all the way back to kind of that long overview video that we did, we'll try and make this one substantially shorter. But here in the main simulator, we've got all this setup that has to happen. But right around here, we actually have a section called the autonomy. And if you open this up in MATLAB, you'll actually see it broken out a little bit better. And in the autonomy, we set up our objectives, which are the gates that we want to visit and in what order. So here I have a list of them, but I've made that list just 1 to 10. So nothing too advanced. If you wanted to go in and see if you can take some shortcuts, skip a gate, take the penalty, but maybe that's faster, you're welcome to give that a shot. And so we've left this objectives open for you to play around with things like that. But this autonomy is just one big for loop, and it's got 3 steps. For the specific objective that you're at, you're going to set that gate ID, and you're going to do find gate, approach gate, and then fly through gate. And then you're going to jump to the next gate. Once you've gone through, let's say you're starting off on gate 1. Once you go through gate 1, the for loop kicks in. You go to the next iteration of that, to gate 2, and you find gate 2, you approach gate 2, and then you fly through it. And we're just going to keep going through that. Now, diving into what these specific functions are doing is kind of the objective for today. I think if I went through line by line on the code, it would be a little bit exhaustive. I think it would probably take 45 minutes or so to go line by line through the code. So instead, let me just kind of hit these from high level, what our objective is trying to do. And so with that, let's first come back to our navigation and look at what's in these folders. Okay. So as we go into the navigation folder, there are the drone commands, and the drone commands are the move drone, turn drone, update drone. Okay. At the more basic level, we've got these 3 that you just saw: find gate, approach gate, fly through gate. And then there's one more that's not at the highest level, but it is still a critical one, and it's search for gate. Okay. So as we dive in, let's actually just start with find gate, and I'll give you its intuition of what's happening here. Okay, so find gate, you pass in the gate ID you want to find, and it's going to return the corners that it sees. Now, anytime you see corners as a variable, corners are going to be the position of each corner. So we'll have an X, Y, Z, or you might consider this an RF U. So specifically, that would be right, forwards, and up. That's the coordinate system that we've chosen for everything. So it will usually have that if it's corners, but projected corners actually loses one of the dimensions. So projected corners is just going to be relative to where the drone's looking. How far is it panning left and right and up? And that's going to be recorded in degrees always. Okay, so you can get a little bit more documentation here, but in general, that's what it's returning. But projected corners does something more, or sorry, not projected corners, find gate does something more. You return these corner values, but you don't actually need to do them, because what's important about it is how your drone behaves when you run this command. Okay, so let's take a look at what this is. We're starting off, this whole command is just a while loop. So while the gate is not found, is how I would read this logic statement. We're going to do these 3 steps. The first one is look at what is currently in the drone's field of view. So step 1, identify gates in field of view. So the drone's got a camera on it with a set field of view, and it's going to take whatever's in frame of that and try to identify the gate numbers of the gates that it can see. All right. Estimate gate IDs is one of the more challenging involved scripts in here. So we're going to save that for a later date. But what I can say it does in terms of output is it it takes in the image and all the corner values that are within that field of view. And that's functionally what our computer vision algorithm will do. And we'll have a whole different series for computer vision and how we're doing that. But right now, it's going to take in all those corner values that would be coming in from your camera and then identified from the computer vision. And it's going to compare what it's seeing to what it expects to see. So what is it expecting to see? Well, the drone has its own estimated location of where it thinks it is. And this is data, you'll see it in the global workspace in MATLAB. And that's the estimated drone location and estimated drone heading. That's where the drone thinks it is and where it thinks it's facing. And based on that, it might have a map of what it thinks it should see. If it thinks it's at a certain location, it would go put itself on that location in kind of the ethereal map, right? And it might hypothesize, I should have a gate. It's roughly right about here, and maybe I'll have one off in the distance that's over here, and one, very close to me that's right here. And maybe there's another one behind that that's here. Okay, so this is what the drone would expect to see, and then it's going to compare that with what it actually sees. So it's going to overlay this kind of in a mathematical way. It's going to kind of overlay this with what gates are actually in view. And when it does that, you might notice some rather obvious parallels. So actually in view is something that looks like this red picture. So this estimate gate IDs is going to go in and say, well, the green ones are from my map. They're from what I know is true about the course. It's data that lives on my drone. And each of those, has a gate number associated with them. So each of those is labeled with a gate number, but I don't know where I am precisely. So when I look at the actual picture of what everything is in front of me, I might be able to do some sort of algorithm that pairs these up, right? It might say, okay, clearly this red gate here, I don't know what it is, but it's got to be gate 1 because look at how close those are, right? So those two are the same. It looks at this pair back here and says, those are about the same size, so they must be the same distance away from me. And they're pretty well lined up, so that has to be gate 6. Here is gate 4. These two look about right. And it even has the capability of looking at this gate and looking at this one right here, number 3, and saying, I don't know, those don't quite line up. Maybe that's not gate 3. And so it has the possibility of just saying, I don't know what this red one is. That's how estimate gate works at a very broad level without getting into the math. So what it returns is it returns the projected corners, all these corners, but it's more than just one gate. So we call this all projected corners. And when you see all projected corners, you can expect this to be a 3-dimensional matrix. So if you dive down into the documentation, you'll see that it's going to be pan and tilt angles for each corner value. And then that third dimension, we stack all of those pan and tilt angles. We get a whole row of them for one gate. And then we do a different layer behind that for the next gate, the next gate, the next gate, okay? And then the other thing that we're gonna do is we're going to return out, parallel to those different layers, we are going to provide, this is pan and tilt for each corner. So this would be corner 1, corner 2, 3, and 4, pan, tilt. So we have this data. Then we'll have another one behind it, right? And this would be, gate 1, and this one's gate 2, or rather what I should say is the first gate, the second gate, the third gate, on and on and on and on. This gate IDs is then going to assign which gate we think that is. So this first gate, we might say that is gate 1. The second gate was gate 6. The third gate was gate 4. Okay, that's how that data would look. Okay, the next thing that's going to happen is we're going to ask the question, do any of the gate IDs, right? So that's this stuff. Do any of the gate IDs that are in view, do they match the gate ID that I'm looking for? Okay, that's going to be the question. If the answer is yes, then we're going to just say that we found the gate. It's here and it's this index. It's this, is it the first gate, the second gate, the third gate, etc. It'll report which one it was. And then we know what corners within the list of all the possible corners are the corners that are associated with the gate we're looking for. If it's not there, so if any of the gate IDs are not the gate that I'm looking for, we will run the search gate, okay? So let's go take a look at that search gate algorithm and what that would do. For some reason, it has some challenges with the back arrow, so I have to kind of play games with the URL. So let's come back in here and let's go look at search gate. Okay, so in search gate, you have an optional input parameter that is your gate ID. If you do not provide gate ID, and that's this first line here, it just says, if the variable gate ID does not exist, is how I'd read that. So these logical statements, I tried to make them very human readable, but just the way the syntax is, you have to bounce around from word to word. So if the variable gate ID does not exist, just turn the drone 10 degrees. Okay, that's what this says. And what that means is if you're not looking for a specific gate, you just want to change the direction you're looking, go ahead and make that 10 degrees arbitrarily. And that happens from time to time. You might get into a position where you're looking, maybe you're at the far end of the course, and there are no more gates in front of you. For 180 degrees, there's no gates. Your drone might wonder where any gate is. It doesn't have to look for a specific one. In that case, it'll just kind of keep turning until the first gate comes into view, and it'll say, okay, what's that gate? So that's how this works. But if for the case that we're talking about, a gate ID is provided, all we're going to do is we're going to go to get gate location. So if you remember from the overview video, get commands, any command that has the word get in it, it's going to be pulling true and accurate information. And in a simulation environment, that can be dangerous because you want to make sure you're representative to the real world. You don't want to cheat in your simulator. In this case, if you follow this train, where is it getting that data? Well, it's not cheating. It's actually just getting it from the map. And the map is where your drone will actually have saved all the corner locations of every single drone gate. Okay, so it's going to go look at the map and pull where that gate should be. And then it's just going to calculate where it thinks that is going to be in real life. So let's kind of take an example of what this looks like graphically. So I'm going to come over here, and here's an example of the map in a graphical form of where everything is. So the map is actually the XYZ location of every corner on our system. So every single gate within the course will have XYZ location of it. And that XYZ is relative to some origin. And this is roughly where that origin is. If you go into the build course command, you'll actually see all the juicy details there. But what's important here is we know where each gate is. And if we came in here and we drew where our drone was, let's draw our drone in red. And let's put him just coming out of gate 2. So we'll put our drone here, and he's looking this way because he's just flown through gate 2. What we want to do is we want to figure out how far we need to turn to be looking at gate 3. Okay, and so this is going to take a couple of tricks to figure out. And to do this, we're going to introduce what we're going to do kind of a lot, which is use vectors to handle all the math. Okay, so if you haven't done vectors a lot, they are extremely useful. If you have done vectors a lot, usually it's in kind of a mathematical class context and less in a hands-on concept. So you might have kind of a negative connotation for them, but they're actually one of the most useful things in modern engineering. Okay, so let's talk about what these vectors are and how we can do them. So a vector is no more than just a data point if you're actually looking at the data. So a vector might hold like this, and it might be some A, B, and C value. So for this code, we are going to use row vectors. So X, Y, Z. That's the way MATLAB likes to use it. You can certainly do row vectors, but things will get a little confusing. So go ahead and use column. But all this data is, X, Y, Z, is it's a point in 3D space relative to this starting status here. Now, you might be familiar with, scatter plots and drawing, points in space. That's perfect. A vector is the same thing, except it assumes a starting point. So the vector that's being shown here would actually start at the origin and go out to this point, A, B, C. And here, the A is going to be some component right. The B would be some component forward. And up. Sorry, my stylus is having a little bit of struggle, and then also I have bad handwriting. So hopefully you'll forgive me for that. So I've drawn those arrows on here. We've got the right component, the forward component is pointing upward on the screen, and then the up is actually out of the screen, if that matters. And so you can pull out your right hand and confirm that's a right-handed coordinate system. So let's talk about these vectors. So we have a vector that's going to go from the origin to our drone, and on the map, what we have is actually vectors that go from the drone, from the origin to each of the corners. Okay. Now, if you take the average of each of the corners of a gate, you just point right at their center, which is relatively convenient. So we have these two vectors that point from the origin. So let's see if we can write this down. Origin to drone, and we have a vector, put a vector hat over that so you know it's a vector. And we also have one that is the origin to the gate. And there's a vector there, okay? Now, what's so useful about these, even though they are basically just points in space, because we're thinking of these as vectors, we can add and subtract these to manipulate them in interesting ways. So if we were to subtract these vectors, what you end up doing, subtracting one vector from another, is the way that you would move the starting point. So subtraction is going to change this first value. Okay, so if we did the origin to the gate, we're taking this vector right here, and if we subtract origin to drone from that, we're going to take this starting point where we start and move that over this distance. Okay, and that's going to give us a new vector, and that new vector is going to be the drone to the gate. Okay, so it's a very easy way to handle how we would come up with, very useful vectors. And the only thing that matters here is that all of the vectors we declare are based on this coordinate system that I'm showing, the coordinate system of the map. And in this work, we call this the global coordinate system. Okay, and certainly you could come up with other coordinate systems, such as a local one that's stuck on top of the drone. And sometimes we'll even have coordinate systems that are relative to a gate themselves. The rule of thumb is you just can't interact vectors that are in different coordinate systems. They all have to be in the same coordinate systems. Otherwise, you're kind of adding apples and oranges instead of apples to apples. So, but there we go. We've now been able to set up a vector that goes from our drone to our gate. And that might be relatively trivial for some of you, but it might be new information for others, or just a new way to think about it. For completeness, let's go ahead and say what happens if you add vectors instead of subtracting them. Adding vectors just changes where they're pointing. So subtracting moves where they start from, and adding moves where they're pointing. Okay, that's the two ways to think about it. Now, once we have all of this, let's go ahead and talk about the next thing that we're going to do. Remember, our objective here is to figure out where we need to point our drone. And we would really like our drone, rather than pointing across this red line, that's its current heading, we want it to actually be pointing across this green line, okay? And to do that, all we really need is we need to know the angle between those. If we know that angle, we could just tell the drone, turn whatever that angle is, and now its new heading would be going along that green line, okay? And this is the next bit of helpful information that we're going to use in the autonomy, kind of higher level autonomy. And that's going to be actually a function that lives in the utilities, and it's called something along the lines of angle between vectors. So let me actually pull that up so you can see where it lives natively. So if we go here, let's come back out to the main simulator and jump into utilities. So utilities are all the mathematical expressions that we have. They're the shortcuts. And here you go. Calculate angle between vectors. And that is what we're going to do. So if we have two vectors, we've got my vector that's my current heading. Let's just call this, for simplicity, we'll call that the A vector. And then we have this green vector over here, points something like that. We'll call it B. So I'm just kind of reproducing a little bit larger over here, what we're seeing right here, okay? We want to figure out what this angle between them are. And to do that, we're going to use a mathematical operator that's called the dot product. You might have used the dot product. I remember when I was kind of early in my engineering classes, I could never keep straight what the dot product was doing or how to take it. Not until I actually started applying it to real skills did it all of a sudden click for me. So let me write down something that may not be helpful, which is the mathematical formula for a dot product. So if we have A dotted with B, that's equal to the magnitude of A times the magnitude of B times cosine the angle between them, which I'll call theta. Okay, so first off, let's talk about magnitude. In this kind of example, magnitude is just how long is that vector. So the green vector is a very long one, and its magnitude is its length. How long is it? Most vectors that I have in here, like this, the red one for the heading, I'm just going to keep a magnitude of 1 because it doesn't really matter. I only care about its direction. I don't care about how long or what its magnitude is. So if I don't care about magnitude, it'll be unit 1. So here is the definition, and you might have heard this is the mathematical definition. You might have heard kind of a verbal definition that the dot product is a projection of A onto B. And that, again, is not necessarily the most helpful description for me, but let's go ahead and show you where that comes from. So what people will typically do is they will put parentheses right here, okay? And they say the dot product A dotted with B is just, if you take the magnitude of everything, it's A times B cosine theta. Okay, well, what does that mean? Well, if we draw a right triangle here, so here's our right triangle, cosine B, right? Sorry, B times cosine theta is just the component of B that's in line with A, right? So it's a projection of B onto A, and then you multiply those two values together. We would call them scalar values. And that seems like a really unhelpful or unuseful skill. For me, the only place I can think about doing projections is if I'm doing like I don't know, a shadow. I want to calculate the shadow of a tree based on the sun. I don't know. That to me was not a helpful, useful skill to memorize. But if I just take the same equation and we rearrange it differently, I think you'll see that this is actually a rather helpful skill to have. And this is just one of the many uses for dot products. But as I do that, let's go ahead and rewrite this this way. So if we come in here and we say A dotted with B divided by the magnitude of A times the magnitude of b. So what have I done? All I've done is I've removed the links of these. The magnitude now no longer matters. I've divided it out. So these are functionally unit vectors. Okay. So if I have A as a unit vector dotted with B as a unit vector, that is equal to the angle between them. Okay, cosine the angle between them specifically. This is much more helpful. I actually like this definition all the time because dot product tells me information about the orientation of angles. And that's much more helpful. There's uses for projections in engineering applications, but as a technique for learning what the dot product is used for, I think thinking about the angle between different vectors is much more applicable because it kind of brings back this mathematical representation and connects it to a geometric representation. And geometry is really easy to visualize. So I like this a lot more. And we're going to use this to actually calculate what this angle is over here. So let's dive in. And again, this is the utility that we've named calc angle between vectors. Okay, so we're going to go in and we will calculate using this expression, A dotted with B divided by the magnitude of A, the magnitude of B. And then all we have to do at that point is then take the inverse cosine. A cosine of that whole expression is equal to plus or minus the angle between them. And this plus or minus is really just a metric of, am I turning counterclockwise or clockwise? Is it a positive rotation or a negative rotation? That's all that means. But if you dive into what a cosine does, you'll see that there's always this plus or minus option to it. Okay, from here, just looking at it, you can tell this is going to be a counterclockwise rotation or a turn to the left. And so it's relatively easy to know for this problem, it's going to be a positive angle. Okay, so once we have that, we can figure out exactly how far away this guy is, and we can turn to line up with it. Okay, so let me clear this off, and we'll go back to the code and look at the next thing. Okay. All right. So search for gate. We will use this estimate pan tilt, which is going to do that dot product. If you dive in there, it'll find the turn angle, and then it will command the drone to turn that far. So that's the whole search for command. The next thing that we want to look at, it's frustrating. The next thing that we want to look at is this approach gate. And at this point, I might go ahead and call the video after this one, because with this last piece of information, you're going to see everything you need in terms of underlining skills. The last one after approach gate is fly through gate, and all it's going to do is fly through the gate. So there's a little bit more to it than that, but I'll let you dive into it. All right, so here there's a lot more to this one. That's why this one's kind of the most complex of all of them. But again, don't let all the math that's happening distract you. Come in and definitely read the step 1, the step 2, the step 3. Okay, step 1 in our goal of approaching a gate is we're going to set an objective on the map. Okay, and so the map I've already shown you here is just our location of where we know all of these drones are. So let's clear this off a little bit nicer. We will. All right. There we go. Okay, so step 1, we need to find an objective point. So if you remember let's start our drone. We've just come through gate 2, which I erased part of it, but we're out here. From a big picture, next step is going through gate 3. But what we don't want to do is we don't want to turn and look at gate 3 and fly to it. And there's a number of reasons that's not the best idea. In this situation where I happen to be, it might be advantageous to fly right through there. That's kind of a fast approach, but you can kind of see the angles aren't very favorable. I might bump into one of the posts of the gate. It would be much better for me to come over to a point that's away from the gate a little bit and fly to that point first, and then turn and look head on to the gate and then fly through it. Okay, and so that's the way that I've written this code to operate, is to set that objective point first and then fly to that. Okay, and that makes this a nice, easy sequence of steps that we can do over and over and over again on a loop. It doesn't matter that I'm going from gate 2 to 3. I could use the same logic going from gate 3 to gate 4. Okay, and to do that, we're gonna, once we know where this point is on the map, we're going to use that same trick that we did in the search for gate, which is come up with this vector that goes from the drone to that objective point, and use my calculate angle between vectors to figure out how far I need to turn. And then I will, let's see here, if we have drone to objective as a vector, and it's this green vector, if I were to take the magnitude of that, that will give me the distance. How far away is that objective point? And then I can use my move drone command and give it in the distance. And it should move my drone as close to this point as possible. Okay, now there's a couple of things you should be aware of. The first is this turn drone, as I turn here, it's going to have a little bit of error. So it might turn me this way or this way. You know, on average, I'm thinking about 5 degrees of variation there. So I have a little bit of uncertainty there. And I also have uncertainty on this distance. I'm going to tell the drone, you know, move forward 15 meters, but it might do 14.5 or it might do 16. It's going to have a little bit of variation. Okay, so that's one thing we need to take into concern is once we execute a turn and then move, we could end up kind of here or here or here. Ideally, we want to be as close to that green dot as possible, but it's not necessarily a given. The next thing that we're going to do is wherever we end up, we are going to be facing this way, and we need to turn over so that we are looking at that gate. Okay, so that's going to be the goal, is we're going to head towards that green dot, turn and face the gate. Now, the last thing is we want that gate to be fully in view. We want to be able for our camera to totally see it so that we can update our estimated location based on that. Okay, and this is all happening within the approach gate script. Okay, so let's go look at that script one more time, and you'll have a context for it. So we're going to set the objective on the map, just like we were drawing out. And then we're going to go to that objective. And as you can see, there's a range that we have to calculate, turn angle, and then we actually turn the drone and move it. And that's where we're going to end up somewhere near that green dot, but not precisely on it. Okay. And then the next thing that we're going to do is we're going to turn to face the gate. And that's going to do, once again, is calculate angle between vectors and then turn the drone so that we're facing. And at that point, we could be done. But I've actually went ahead and added a fourth step. And that fourth step is checking whether or not the gate is in view. Because if the gate's not within view, because there's that little bit of uncertainty of where I am, if I am, let's say, this point right here, and I turn to face the gate, on my next step, which is fly through the gate, I'm going to fly right through the post of that. And that's not terribly helpful. And even if on my next step, I have a little bit of an algorithm that says, no, look towards the center of the gate, I might be coming in from a very oblique angle. And all in all, I still think I'm at this green dot, right? I know that I'm not going to be there precisely, but I assume I'm close to it. So what we really should do is wherever we land, we should back up a little bit to make sure that this gate is within the field of view. And once we do that, we can lock down precisely where we are. We know we're close to that green dot, but we don't know precisely where we are. And that's going to be important. So that last step right here is the check to see if it's visible. And as always, that's going to use the estimate gate IDs that we already talked about. And if it's not visible, so if the gate is not visible, move the drone -5 meters. So move it backwards 5 meters. And then that's going to send it to the top of this while loop. And we're going to check, is it visible? If it is, we jump out of the while loop. If it's not, we keep backing up 5 meters at a time. Okay, so that's the logic here. But there's one thing that I think we should probably dive into that is substantially different from what we walked through previously. And that's in this step 1. There's a couple of terminology points that I want to explain. So here, this is where we are setting that objective on the map. And I think that just requires a little bit more discussion than what I've given it. So let's come over here. Let's clear off, oops, not mean to zoom. Let's clear off some of these talking points. We'll clear these off. And we'll redraw that line. So there's gate 3. It's a little less smooth compared to how it was before, but we'll make it work. We'll delete that. Okay. So we come in, we have set our objective to be right here, but how did we actually do that? And this is the last kind of tip and trick that I'll show you, because it does require, again, a little bit of that vector manipulation, linear algebra skills, which not all of you have had. So how do we find a point that is away from the gate? And this one really comes down to another trick. We talked about the dot product, but there's another mathematical operator that we use in linear algebra that's called the cross product. That's not a B. Good try, but not quite. So you can dot 2 vectors together, and that gives you information about the angle between them. But you can also cross these vectors together. And crossing them has a mathematical explanation that we can talk about. So if this was an A vector and this was a B vector, the cross product is going to give you information about the area that these 2 vectors fill up, right? So if we parallel, make a copy of this A here and a copy of B here. Okay, this area is related to the cross product. So the cross product is actually going to give you this area, right? And that kind of makes sense. If we have multiplication of 2 links, like even in just standard geometry, if we have these 2 links and we turn them into a square, A times B is the area of that square. The same concept is applicable here with dot products, but we're not requiring that these vectors are edges of a corner. They could be any angle separating them. And the cross product is still going to give you that area of whatever parallelogram this generates, okay? But it's going to give you that area as a vector, and that vector is actually going to be orthogonal, which is a fancy word that means 90 degrees away from both A and B. So it's going to be the area as a scalar times some normal vector, okay? And so this is going to be the equivalent of sticking out away from those. So if these 2 vectors are on the surface of the screen, the normal vector would come out of the screen. And you can actually check that using a right-hand trick. So if you line up your hand with the A vector and you rotate it towards the B vector, the direction of your thumb, if you're using your right hand, is the direction that your normal vector will come out. So if we did, B rotated to A, you'll see that my thumb's pointing into the screen. It would just go the other direction. Okay. Now that is kind of interesting. What I don't care about for this problem is the area. I could care less. One way to get away from the area is if A and B are both a length of 1, then 1 times 1 is 1, and it kind of disappears. So let me give you a variation of this. If I have something instead of A times B, if I did A cross B divided by the magnitude of A and the magnitude of B. So by not putting the arrows on top, I'm saying that these are just the scalar part of it. That is going to equal a normal vector, okay? Okay, now what's the purpose of this? Well, what's great about this is I can set up a vector between various corners of the gate, right? If you remember, the map has vectors from the origin to every corner of each gate. And so, if this is my gate, and I have a vector to each of these corners, what I can do is I can actually take the difference of any two of those. So let's do from this corner to this corner is 1, and this corner to this corner is the other. That's 2 vectors that are within the plane of the gate, okay? So if we make one of these the A vector and the other one the B vector, and we take that cross product, let's see here. Let me actually flip it around backwards so that my analogy works. Let's call this one the A vector and this one the B vector. So if we do A rotating in towards to B, to do that rotation, I think it's a little bit more helpful to kind of move them off the gate. So B goes up and to the left, so this is B, and A goes up and to the right, so this is A. So if I say A, and then I rotate towards B, my thumb is coming out of the screen. And I can use that, now that I know this normal vector, that vector, if I were to draw it on the map, would point this way. Okay, so what you can see is what I'm going to do is I'm going to take my origin value, go to the map, and get a vector that goes to the center of the gate, right? And the center of the gate, I can just use the average of all 4 of those corners to get to it. And then I want to take that, so this is the gate location vector, and I'm going to add it to this cross product of values. Okay, now this cross product, all it is we're going to refer to that as the gate pose. Pose is kind of one of these computer vision language jargon. It just is the direction it's facing, right? So it's the normal vector. So I'm going to add that vector, and that's going to change where I'm pointing, right? So when I add those 2 together, I come off to the end of the red value. Now, because the normal vector is only a length of 1, in this case, it would be 1 meter, that might not be far enough away. So I'm just going to multiply it by some offset. And whatever that length of offset is will dictate how far away from the gate my green dot is. Okay, so if we go and review this in the code, this is what you'll see. We get a vector that is the gate location. So this is from the origin to the gate. Then we're going to get gate pose. This is also information that comes from the map, and it's going to use a cross product. Now we have those 2 vectors together. And my objective, again, this is a vector, is just going to be the vector from the origin to the gate plus the vector from the gate away from it, the normal vector. And how far away? By the magnitude of the offset, okay? So that's all it is. Hopefully that breaks it down into pretty good chunks. Once you have that objective mapped out, following in on step 2, this is going to be very similar to stuff that we had to do for the previous step of identifying and finding the gate. We have to calculate angles between vectors to turn. We're going to move the drone by some range, and then we're going to turn back and face the gate. And if that gate's not in view, we should back up a little bit. Then for completeness, let me just go ahead and show you that one last step, which is the fly through gate command. All right, here's fly through gate. All that we're going to do is we're going to align with the gate. So, and my chat is exploding. Sorry, my students are a little ambitious. But if here's a gate and my drone ends up landing right about here, if we fly straight forward, we might not end up going through the gate. Instead, we're going to want to identify the center and turn to face the center of the gate, okay? And that's what this align through gate is doing. And you'll see it's nothing more than what we've already done. We're going to calculate the angle between where the gate is relative to the drone and where the drone is currently heading, right? So vector to gate, estimated drone heading. So this is all stuff we've seen before. We're going to do a check to make sure that in that same logic, if my drone is here and it was looking this way and to turn to go through the gate, if this is a large angle, we know that we're going to come in a very oblique angle. And so I basically just set a threshold. I say, hey, if this angle is more than 40 degrees, we are not in a good orientation to fly through this gate. We should approach the gate again, okay? And so if we do that, we're going to reset up that objective, and we're going to turn and fly, hopefully close to that objective, and then rotate around until we're facing the gate in a more head-on approach. This gets triggered occasionally. It really depends on which gate you're coming from and which gate you're going to. But this is just a little bit more help to make sure that your algorithm works in every single situation it could end up in. And the last thing that we're going to do is we're going to fly through that gate. So we're going to figure out the range from the drone, where it thinks it is, to where the gate is on the map, plus some offshoots. We want to make sure we make it all the way through that gate. And of course, there'll be a little bit of random noise there. All right, so that's everything. It's a bit of a water hose, but I wanted to document it all in case vector manipulation isn't something that you've done before. Strongly encourage you guys, always draw it out. I've got a lot of code that looks like this in this work. And if all you're seeing is a lot of mathematical expressions, it's going to be hard to follow. And if it's hard to follow, then you're going to have a hard time inventing your own modifications to it. But what I wanted you to see is I wanted you to see that each of these is really got a graphical representation to it, right? Starting from the origin to some location. And as you graph that out, you actually start seeing some things as more navigation-based ideas with arrows and vectors and directions, rather than just numbers and mathematical operators, okay? So I wanted to show you how to start thinking about this so that as you dive in and make your own modifications, you're able to engage the code with the way it's written. So hopefully this is helpful. Certainly reach out to me if you guys have questions. I would love to walk you through the code that I've written, and hopefully you guys can look at it, come up with your own creative solutions, and make it better. But that's it for this one. Again, sorry it's so long. I try to cut it down, but I wanted to make sure that I didn't cheat out and not describe vector addition and subtraction, dot products, cross products. And hopefully this gives you a kind of a hands-on application that gives a little bit more sense to these mathematical operators that you might have used before. So with that, we'll meet you into the next one later.